Okay, welcome everyone to today's CDAC webinar. It's a pleasure to introduce today's speaker, Camille Bernal-Choban from the University of Illinois at our sister campus at Urbana-Champaign. Camille is a materials physicist with an expertise in determining the thermodynamic properties of materials using techniques such as phonon scattering of neutrons and first principles methods. Camille received her bachelor's in nanoengineering and mathematics and applied science at the University of California, San Diego. She then moved to Caltech for her PhD, where she worked with Brent Foltz and began her studies of first principles methods and neutron scattering techniques. And at that time was partly supported by CDAC, and in fact was a presentation winner at one of the annual NNSA program meetings. Last year, Camille moved to UIUC and is a distinguished Granger postdoctoral fellow there, and is now focusing on electron loss spectroscopy and X-ray neutron scattering methods to investigate hidden orders in condensed matter systems. Today, Camille will give us an overview of some of her thesis work, including some of the work she did with CDAC. So welcome.
Thank you, Russ, and thank you for that great introduction. As Russ stated, today I will be sharing my PhD research, which does combine a lot of academic journey, experimental and computational techniques. And in this particular instance, I'm going to hopefully tell you a story about how we can better understand the fundamental origin of the latent heat of melting. So let's get started. All right. And of course, my PowerPoint, there we go, perfect. Okay, sorry about that. I'll start this talk after a couple mistakes by motivating our study on the latent heat of melting by highlighting one instance where it plays a key role in technological or potential technological applications. And then I'll move into a more thermodynamic perspective where I will define a thermodynamic definition of melting, which many here are probably familiar with, but then I'll take it a step further and restructure that to include atomic scale contributions and talk a little bit about how we can actually measure those and quantify them. And once I've made that connection between the macroscopic and these atomic scale contributions, I will go over the techniques used and the analysis that were developed by myself and my colleagues at Caltech to really look at the fundamental origin of this latent heat of melting and how our findings contribute to understanding of melting need to be done to get a better understanding. Now, I wouldn't be surprised if when I said latent heat, a diagram such as the one shown here, where we have a solid on the left, a liquid on the right, and it is a function of energy content and temperature, comes to mind. And there diagram for just chosen to elongate the latent material. So this is the energy that you can put into a material and it can absorb all of that energy until it fully liquidized. And there's actually interest in harnessing this stored energy in a class of materials called phase change materials. We can one day integrate them as a passive energy source into existing solar grids, existing infancy, although some applications such as in HVACs do exist. But really to do this, we're really not there with materials. And that's because in order to get these types of materials, one of the requirements is high energy density and high latent heat. But while it's relatively straightforward to test a bunch of these and measure these latent heats, from a fundamental point of view, we really don't have a complete picture yet. And I'm hoping to add a little bit of insight to that picture today. So with that being said, I'm actually going to go back to a simplified plot of free energy as a function of temperature, where now we have some really simplified free energy curves for the solid, F sub S, and for the liquid, F sub L. And note that at the melting temperature, T sub N equation called, and actually go back and derive the thermodynamic expression, which many here probably are familiar with, for the latent heat of melting or the latent heat of fusion. And this is a product of the melting temperature and the difference in the entropy between the liquid and the solid state. Now, this difference in entropy or disordering of the system actually has a name. It is called the entropy of fusion or the entropy of melting. And it is this term that can actually be written out as a sum of atomic contributions. And for the purposes of this talk, I will be talking about monoatomic non-magnetic systems. But I do think this analysis or this type of analysis could be extended to compounds and magnetic systems in the future, and I will revisit this at the end of my talk as well. But for now, let's go ahead and rewrite this entropy of fusion, the total entropy of fusion, into a sum of atomistic components, where we have an electronic contribution, a configurational contribution, and a vibrational contribution, whereby the electronic contribution, I mean how the electron filling changes between the liquid and the solid state in a material. By configurational, I mean how a crystalline solid turns into a liquid phase. So having a very structured, ordered material going to something that is more dynamic in nature. And speaking of dynamics, we also have a vibrational component. And I'm going to roughly define this as how atoms move about their equilibria, but I'm also going to extend this from the typical solid into the liquid regime. So I have here an animation for the solid phase, but you can imagine that these atoms are moving around in the liquid, and although they have maybe some points that they diffuse to, they will still have some motion about some temporary equilibrium point. Now, intuitively, one might expect to have the configurational component be the main component to this total entropy of fusion, because every atom, every system that we know that will go through a process like this. And in fact, this is more or less the idea between a rule or behind a rule named Richard's rule, which is an empirical rule that states the entropy of fusion is about that of the configurations. And this was estimated to be about 1.1 kb per atom by taking the total entropy of fusion, plotting it against atomic number, and kind of taking this maximum value in a histogram, which I've shown on the right. But as you can also see from this plot, especially the one on the left, there are a lot of elements that break Richard's rule, so they don't obey this. And one of the questions I wanted to ask is, okay, why is this? What other sources are there? And to do that, I actually had to go back and relook at our summation for the total entropy of fusion. Again, it's a sum of the electronic, configurational, and vibrational components. And let's just for now assume that Richard's rule is correct and that we will have a configurational entropy of fusion that is about 1.1 kb per atom. So that's taken care of. That is what our configurational entropy is going to be. It clearly doesn't explain everything based on the previous plot. But we also know that the electronic entropy of fusion should be relatively small. And we know this because the entropy, the total entropy of fusion across all the transition elements really isn't as different as you might expect if you had a sudden change in this electronic configuration. So that leaves us with the vibrational entropy of fusion, and it gives us at least an idea that this might play a bigger role than one might expect. And one of the most important things about this, at least from my perspective as a neutron scatterer, is that we can measure this. Very specifically, we can measure this with a technique called inelastic neutron scattering. And this is a very simplistic diagram of this. I'll get into more of the details later, but for those who aren't familiar with inelastic neutron scattering, I do think it's a cute little animation. So we have a neutron, which is a heavy uncharged particle, come in and hit our sample with a specific incident energy or initial energy and initial momentum. So here those are E sub I and K sub I. And this will impart some energy and momentum into our sample and then fly off with a final energy, E sub F, and final momentum, K sub F. But what we're really interested in is looking at what is happening with the sample itself. So what we're really interested in is the change in momentum of the actual sample, because this will actually give us a distribution of the vibrational dynamics in a material. Doesn't matter what phase that material is in. Okay, so now that we maybe hopefully have an idea of what this technique has the power to do, what do we want to use it on? And this is where the question gets a little bit trickier, because we do have to choose a variety of elements that properly represent the distribution of total entropy of fusion across the periodic table. But we also have to make sure they're compatible with something called the neutron scattering cross-section. So we have to make sure that we will actually see something from the neutrons and they don't get radioactive, or at least too radioactive in the process. And we also have to make sure that our furnace can actually get high enough to melt these in situ. And for us, that answer was germanium, tin, lead, and bismuth. So germanium has a anomalously high entropy of fusion, where lead is much closer to the value predicted by Richard's rule of 1.1 kb per atom. And you'll notice here that I have some black circles, black crosses. These black crosses are elements that we revisited in our computational work later, so I won't be talking about them as much, but they will make an appearance. Okay, so now that we have the elements that we can look at, how do we actually do this in situ melting process? And this actually took a bit of time to figure out, but it turns out that you can put the desired amount of material that you want into evacuated quartz ampules. So these are sealed. And then just as a secondary containment, we can then align them in this vanadium foil sachet. And we put them in the path of our neutron beam. And when we take them out from this, as shown here, what we find is that our sample did indeed melt, and that we did get enough sample in here so that we fully filled the beam. So the beam size is about 50 millimeters. This is about 2.5 inches, and they're roughly equivalent. Now, all of these experiments were carried out at beamline 18 at the spallation neutron source, located at Oak Ridge National Lab. And very specifically, beamline 18 is known as ARCS, which is the wide angular range chopper, a direct geometry time-of-flight spectroscoper. And the principle behind this is that instead of choosing which momentum transfer you want, you actually choose the incident energy you want. And you do this by breaking up a pulse polychromatic beam that comes from your neutron source, and you pass it through a Fermi chopper, which rotates at a particular frequency to give you the incident energy that you want to hit your sample with. And one of the really nice things about ARCS is that we have this very nice large detector here that will record the location and the time at which a neutron event is detected. And if this makes no sense, that is okay. I have a pretty picture of a flattened view of this that might make this a little bit more awe-inspiring than I'm able to actually tell. So again, this is a flattened view. They are in a cylindrical pattern. And I'm going to play this at about half of the real-time speed of collection. And we have a polycrystalline Bragg peak that we can see here. But what we can also see is we can also see a lot of other intensity that really doesn't have a defined shape. And these are our phonons or our vibrations in the case of something like a liquid. And so my job was to take all of this data for both the solid and the liquid and get it into a way that we could actually interpret this and then relate it back to that vibrational entropy of fusion, and then from there, the latent heat of melting. So that's what I'm going to walk you through right now. So the first thing for this data analysis workflow that I developed was looking at the data in a way that we can better interpret. So there are a lot of different neutronic. One of the ways that is pretty common, or I guess standard, to look at your data as a first pass is something called the dynamical scattering factor, or an S of QE. And here I have the S of QE for germanium at a temperature of about 1200 Kelvin for both the solid on the left and the liquid on the right. And each of these plots is a function of the magnitude of momentum. This comes from the fact that we have a polycrystalline sample rather than a single crystal. So we really only get the magnitude of momentum transfer here. And we also have our energy gain or loss with respect to the sample. So I'm just going to show a bunch of these briefly for each of the elements, and then I will come back and explain how to interpret the intensities that is appearing in each plot. But for now, I just want us to look at differences and compare them. So for germanium, we can very clearly see that the solid and the liquid vibrational spectra are different. We also note that for tin, we have the same observation, the solid and the liquid are different, which again, not entirely unexpected. We are completely changing the structure and dynamics of these systems when we melt them. But what we can start to notice as we go through more and more of these, and I'm going to jump back to germanium real quick, is that between the different elements in the solid and the liquid phase, we also see differences. So pay attention to the liquid S of QE for germanium. It is significantly different from that of the tin when plotted on the same scale. And lead is a little bit different than tin and germanium as well. And bismuth also has some unique features to it. And so this gives us a hint that we probably are going to see some vibrational differences in these, which is encouraging for us. So this for us was like oh, this is good. We should continue with this analysis type of moment. But for those who don't know how to interpret this, this looks like a bunch of spaghetti plots. And so that is what these next few slides are for. So we can think of this zero energy transfer line as the elastic line. So there's no energy transfer here, but we do see, at least in the solid, these very bright spots. And these are exactly your Bragg conditions. Very specifically, they are the Bragg conditions for germanium in this case. And they actually do give us a nice diamond cubic structure if we were to go and look at where these appear in momentum space. This other intensity that is away from zero is the vibrational modes, or the lattice vibrations. Now in solids, these are called phonons and they are quantized. And I just have an example of a mode shown here, but in reality, there are 3 times the number of atoms in any unit cell in terms of these quantized vibrational modes. So for germanium, crystalline germanium, I should specify, that is 6 modes. You can kind of see that maybe there are 3 modes here and a couple up here as well. So this is from a very quantized kind of physical equation type thing, but there is another way we can view this. And I am bringing this up because we will come back and visit this later on. And that is just looking at it in terms of what's happening on a potential energy landscape. And in this case, for germanium, we have some type of periodic in one of these on average. But depending on the curvature, the atom will travel a certain amount, curvature and temperature, I should say. The atom will travel a certain amount kind of about and up these wells. So that is the case for the solid. A lot of the analysis work to get phonons out and interpret phonons has already been established. But what is less established and what I spent most of my PhD research doing was actually looking at how to interpret this S of QE on the right for the liquids. And unlike in the solid, we no longer have an elastic line. We have something called and we have this because our atoms now don't have a fixed equilibrium point. They can change it through the process of diffusion, which I've motivated here by a binary type system. And we can see that this line here really doesn't have a defined shape. There's intensities that might grow out here. There is a large, for lack of a better word, intensity blob here, which roughly corresponds to what we think is the interatomic distance. But other than that, we really don't know what exact form this will take. And we'll get a little bit more into this later. But what we also have hidden amongst this is we do have some vibrations at temporary equilibrium points as kind of motivated by these white circles here. So we have both of these in the liquid. We might not be able to interpret them as phonons per se, but they are some sort of vibrational mode. And again, returning back to this potential energy landscape theory, we can now envision this as some kind of randomized potential wells. And atoms can, of course, vibrate within these wells, but they also can now get enough energy to traverse these wells. So my next step is, okay, we know solid, we now have to look at each Q cut point by point. So that's exactly what we are going to, and by Q such as this. And that was that you had to look if you see where this overlap region is between the quasi-elastic peak and the vibrational modes. And in fact, for just germanium alone, this is a representative screenshot of all of the data that I actually did have to run through. I'm going to pick out one here that I know results, but many of them also did not work, which was discouraging at the time. But again, back to the actually identical spot. So Q cut, so it is again just the intensity along this vertical line here at this specific point. So we have energy, intensity, our vertical axis. And what I want to see is there any vibrational intensity in this area here that we can extract? And the answer is yes. And it is yes because we actually know a functional form, a Q-dependent functional form, mind you, for the quasi-elastic neutron scatter. And that is given by this equation here. It is Lorentzian-like, where we have our width dependent on Q part here. And what I can do is I can use this equation, convolute it with our resolution function from the instrumentation, and I can then perform a fit to this, get that fit out, and subtract it. And when I do that, I actually do see that we have some leftover intensities that are vibrational in origin. And so now that we know, or I've confirmed that we do have this vibrational spectra in liquids, how do we actually use this? And the way we actually use this to get that vibrational contribution to the entropy of fusion is we create a process to get a vibrational density of states. And what a density of states is, it is a relative, it's a representation of the relative intensity of different vibrational modes in a material. So kind of where can these vibrational modes exist? And we can take advantage of some of the tricks that are known for solids in this case. So for example, we do know that the intensity for a single scattering neutron event should be proportional to the density of states G sub V. I do want to pause here and stress that we only really want contributions from a single scattering event. And by that, I mean the process I described earlier, that cartoon of neutron scattering, and that we have a neutron come in and excite a single vibration or vibrational mode, and then scatter out of the sample. In this case, we can have something called multiphoton scattering, where we will have a neutron come in, excite more than one vibrational mode, and then scatter out. And we can also have something called multiple scattering, where we have a neutron come in, hit the sample, scatter to another part of the sample. So in this case, maybe the left to the right side of those tubes I showed out and scatter to the detector. And this is an issue because it can make an event that is maybe elastic in nature no longer look elastic, or an event that is no longer, or that should be inelastic, look elastic. So we do have to be careful about interpreting that. But assured, the multiphoton, we can actually integrate that into our iterative algorithm to get a density of states from the vibrational spectra. And the way we do this is, honestly, we start with a guess. So we will guess some density of states, usually based off of something like a Debye model or the velocity for a liquid. And then we'll calculate the expected vibrational intensity from that. We'll then compare our calculated intensity with the actual experimental intensity and use those to generate another density of states. Now, if that density of states is really close to the previous one, that's great. We can stop there. But oftentimes we do need at least 3 iterations to actually go back and get to a point where our guess agrees with the previous iteration for that. And again, multiphoton can be included in here, and it often is. I don't have time to explain that for the purposes of this talk, but again, you're free to ask me after. Okay, so now that we have our intensity, and we know it's proportional to our density of states, we do this iterative process and we get out our vibrational density of states for all the elements that we're interested in both the study should ask is, okay, this is great. We have some representation of our vibrational modes in both phases, but what do these mean? And that is kind of what I asked myself as well. We can kind of see that for lead, we have a small increase in where the highest vibrational mode can exist. And for germanium, we have a pretty significant decrease. So we already see that there are going to be differences between these elements. And if you recall way back towards the beginning of my talk, where we had germanium and lead on that total entropy of fusion, lead was pretty close to Richard's rule, but germanium deviated a lot. So maybe this is telling us something. And we also here have bismuth and tin. Tin looks more or less the same, but we do see some change in bismuth as well. So let's take kind of what we expect and what we've learned from here and finally put them together so we can get that vibrational entropy of fusion, which again, we can then relate back to that latent heat. Okay, so how do we get from our densities of states, which was already quite a step to get to our vibrational entropy? And the way we do this is through this expression here, which many of you in the audience might be familiar with. And we'll do this for both the liquid and the solid of the element at our melting temperature T sub n. For those who aren't familiar with this equation, this n sub e is the Planck distribution or Planck occupancy factor, whichever you prefer. And this right here is essentially the oscillator contribution for a specific energy. And you can see here that for about 1200, which is the melting temperature of germanium, we do have a significant amount of this. And this is because all of these modes are activated. What we also have, and this is actually a key thing to have, is we have the full vibrational density of the states for both the solid and the liquid, including the anharmonic terms. So although this is a harmonic type expression, since our density of states does include anharmonic contributions, our vibrational entropy itself will also include some, at least up to second order. So now that we have these, we can multiply them together for each energy, continue this process, and then add everything up. And once we've done that, we can start comparing things. And that's exactly what I've done in this plot here, where again, our total entropy of fusion is plotted on this vertical axis, and we have the different elements we were able to look at with neutron scattering on the horizontal. And for germanium and bismuth, we do see that there is a significant amount of vibrational contributions to this total entropy of fusion. For tin, it's maybe not as prominent, but it is still there. And for lead, which if you recall, actually had an increase in that vibrational density of states when it melted, we do see that this contribution is negative. So that was kind of unexpected, but this is what we got with the error bars. And we also noticed that this still wasn't enough to really explain everything, even if we added in an extra 1.1 kb per atom for that configurational for Richard's rule. So that made us sit back and think and actually do some molecular dynamics with interatomic potentials. And what we found from here, for the elements that we were able to do both experimentally and computationally, is that we did get pretty good agreement between our experimental and computational results. And even with our lead here, which, if you recall, was negative, we are actually able to reproduce this negative contribution with our computations as well. So this is something that we do think is real. Another good thing about having these computations is that we can now pretty confidently say that we do have this extra vibrational contribution, but in addition to that, there is a configurational contribution that is greater than that predicted by Richard's rule for these elements as well. And as we expected, this electronic contribution is pretty small. Okay, so now that we have kind of more of the pieces at once, in terms of what's happening on an atomic scale, we sat back and we kind of looked at just drawing a basic line across these diagrams. So we noted that for the elements that had a really high total entropy of fusion, we did generally have more of this vibrational and more of this extra configurational. And this was also true in our computational results, which you can see lithium here still follows this as well. And we started plotting correlation plots to better understand what was happening. And it turns out that the vibrational entropy of fusion actually scales with the total entropy of fusion. And if we fit this with a best fit line, we actually find that its zero is 1.2 kb per atom. And this is really interesting because it's remarkably close to the value predicted from Richard's rule, even though it's an empirical rule. And this made us start thinking and say, okay, well, what if Richard's rule was true for any given element? And what if this equation is also true as well? That would mean that we can write two equations, one from this best fit line that I just showed, and one from Richard's rule. Assuming this 1.2 were true, this would be zero. It is not zero, there is some excess here. But this left side of the equation on both is equivalent. So after just a renaming of this variable, we can actually say that, or we can equate these two. And what this comes out to me is that our excess configurational entropy of fusion is about 0.8 of the excess vibrational. And this is true of all of the elements that we were able to look at. And this is really interesting, at least from a potential energy landscape theory. I told you this would come back. Because it means that in the solid state, we have something that where we have a minimal or lesser number of basins, but they tend to be very deep and have a lot of curvature. But upon melting, we actually see that we not only have these shallower types of wells, but we also have much more of them. And if we sit back and think about it, this is maybe not entirely unexpected, but I believe this is the first experimental evidence for actually seeing this and finding this. So that was really exciting. So with this result, I'm going to move into the summary and the conclusions, and then I'll talk a little bit about where I think this kind of direction can go. So again, we started out looking at the latent heat and how that is related to this entropy of fusion. And then we went and looked at a technique called inelastic neutron scattering, where we looked at how scattered neutrons can actually measure our vibrational modes in both the solid and the liquid phase. And we then went over how to interpret the results from such a neutron scattering experiment in both the solid and the liquid phase, and kind of how that related to a potential energy landscape perspective. We then went back and discerned the vibrational spectra from each of these elements. I didn't show all of them here, but rest assured I did do them. And then for each element, we have our respective densities of states for the solid and liquid, and we use these to extract a general trend for the relationship between the vibrational contribution and the total entropy of fusion. And we were actually able to relate this back to the physical process of melting itself, which I think is pretty cool. So now some questions and comments that I have going forward is that one of the things that I would like to look at is compounds. Very specifically, I think looking at a compound that has a higher melting temperature than its constituent elements would be really interesting to see how these atomic scale contributions change or evolve over this. One potential contender for this is aluminum antimony, which has a favorable neutron scattering cross-section, and we also can reach these temperatures in our furnace, so that's promising. And I would also like to look at some that have a lower, or compounds that have a lower melting temperature than their respective constituents, because I think that would give us further insight into this melting process and maybe how we can go about better understanding latent heat and melting. Magnetism might also be something to include in the future, but I don't quite know how to get that in there yet. So for now, pending directions here, but I would like to stop here just to allow some time for questions. And yeah, we'll leave it at that.
Thank you very much, Camille, for a very nice talk. Very clear, very elegant work. So the talk is open for questions, comments. Just raise your hand or unmute yourself, speak up. Okay, Dongzhou, go ahead.
Hi, Camille. Thank you for the very interesting talk. Yeah, I did learn a lot from this talk. So I have two questions. So first is that how do you define the phonons, especially in the liquid? I mean, from my understanding, if I understand correctly, classically people believe that phonon is a collective motion of atomic vibrations, but in the liquids, if I understand correctly, I mean, the atoms are actually moving around and they don't even have an equilibrium position. So I just want to hear how you understand this.
That is an excellent question, and that is something that we did puzzle over for a bit. And I hope I didn't make this mistake throughout the talk, but I did my best to not mention the word phonon with respect to the liquid. It is some type of vibrational mode, and we know this because if I can go back to an S of QE here, 1 second. So maybe this is a better representation of this. So one of the reasons that we know that we are actually looking at a vibrational type mode, I'm not saying it's a phonon, is that we are measuring something that is, and seeing something in terms of intensity that is very clearly away from zero. So I haven't removed the Bose factor from here yet, so it looks flat, but we do actually see some shape here that will give us a density of states. So again, I would not go so far as to necessarily call it a phonon, but it is some sort of vibrational mode in the liquid.
Mm-hmm. Okay, yeah, I have a second question regarding specifically this figure here that you show on the right, the germanium one. So you mentioned that there are not only, I mean, single, I shouldn't call it single phonon, but since you use the word phonon, single phonon and multi-phonon scattering. In the right figure, how much of the, like, for example, the Q equal to 1.65, around like 10 MeV is there, about 10 of 11 counts. How many of them are supposed to be from the single phonon contribution? How many are actually from the expected from the multi-phonon scattering?
So very specifically, the multi-phonon scattering versus the total intensity here, not the, yeah. Okay. So I actually don't have a direct value for you because when we do this iterative process, we actually do some scaling and normalization. So I don't have maybe an exact comparison for you, but when everything is normalized, we do assume our 3N modes in order to get a density of states out. So I can't really comment on how much of this is actually, or how much of the intensity is removed from it. I could look into that if I wanted to go back to the data itself. I do have it, but since everything was normalized, one of the other issues that was not maybe expected is that we do have to fit this. So that's why this looks so smooth compared to this here. So we do have to remove some of the lower energy stuff. And this actually was the more difficult problem is that we had to remove some of the intensity that we had from this single scattering process, or whatever you would like to call it. But if you want me to follow up with that, I can look into that.
Okay, thanks. Yeah, that would be great. Yeah. Okay, thank you so much.
Can I ask a question, Russ?
Go ahead, Urshan.
I want to follow up on Dongju's question. The density of states that you have obtained from the thermal measurements, did it include multiphonon elimination, or these are just integrated without any reference to multiphonons? Especially near melting, multiphonons could be a significant contribution.
So it is included when we do this comparison. I actually have a full backup slide on this, just in case somebody asks about multiphonon scattering. So we actually do go through all of these different iterations for multiphonon within that in order to compare our calculated intensity with our experimental intensity. And this is your question, correct?
Yes.
Yeah, okay, making sure. And so we will actually go through this entire process, starting out with a guess densities of states, and we will generate multiphonon and then remove that from our final iteration. So it is fully removed when we go through this iterative process.
Yeah, I mean, one difficulty or difference, I would say, not difficulty, between neutrons and X-rays is that in the case of X-rays, the energy is so high that if you keep the detectors constant, Ki and Kf, then Q1 is always constant. Whereas in neutrons, your incident beam energy is comparable to the phonon energies. And that's a huge difference between X-rays and neutrons. So in particular, I have tin in mind, because in tin density of states can be measured very accurately with nuclear resonance scattering, and has been actually published in several different forms.
Yes, and there are multiple scattering corrections, or sorry, not multiple scattering, multiphonon scattering corrections that have been developed for that. You're absolutely correct. They are a little bit different in terms of the method. I think you use a Fourier transform method versus an iterative process typically. But this is the one that is typically done, at least within the incoherent approximation for neutrons.
Thank you.
Thanks, Urshan. Adam, do you have a question?
Yeah. So first off, great presentation. Second off, so you had a very interesting animation around the middle of the talk. It was about what looked like atoms have experiencing like tunneling events in like you had I think you were talking about the liquid vibrational density of states, where you had a sublattice that was liquid. Yeah, that one.
Yes.
So yeah, I guess my question is, are these I've forgotten by now, but one, are you plotting like a sublattice with a melted like liquid inside of it?
So this is not a truly representative picture of what's happening. It is just the closest I could find to giving people a guide to the eye and saying like, oh, something could happen where maybe it's locally locked into some configuration and it's vibrating within there before it's able to diffuse. And that vibration within that local configuration is what we would consider this vibrational motion in a liquid.
Okay. Yeah. The reason I'm asking is because I think there's something very similar to that picture happening in the materials I'm studying right now, the rare earth hydrides.
Unfortunately, hydrogen doesn't work well with neutron scattering, or I'd offer to test it.
Of course. Okay. great. But a simple question. Do you find that the vibrational entropy is dominated by the lowest energy phonons or vibrational modes for what you observe in liquids?
So there is, as I'm going to mispronounce this poor person's name, but the first person who asked a question, they brought up like, what does it mean to actually have some sort of phonon-like thing in a liquid? And again, I hesitate to really call it a phonon, is some vibrational intensity. But
sure. I'm happy to call it whatever, diffusive mode, breathing mode.
okay.
Yeah.
So one of the things that was actually something that I spent quite a bit of time looking into is, do we actually see distinctive modes in here, or is it really just kind of like a general up and down? And I had to do a lot of scaling for this because not all, and I must have hidden this better than I thought I did. But one of the things that we had to kind of do is we had to pick and choose which key we were at. And this is because of that overlap between the quasi-elastic peak and our vibrational spectra. So in some cases, the quasi-elastic peak just got so broad that it was just all quasi-elastic and we couldn't make anything else out. So we had to do a series of different scalings and go check these with known values of velocities to make sure this lower energy part actually behaved as we expected. And we did a couple of different scalings for this, took the differences that way as well. And they all agreed within our error bars. So that's kind of when we're just like, okay, this is really what they look like here. I don't know if I would call them particular modes.
Sure, yeah. But my question is about the contributions at different energy scales to the vibrational entropy.
So, for example, does this determine where this is going to go?
So when you raise temperature, you expect entropy effects to dominate in a system.
Yes.
And it looks like in the liquid form, this density of states is being pushed down in energy. So it would seem to me that the vibrational entropy is being raised by turning into liquid form because the density of states is going down in energy.
Yes. So that process, yes, we actually did expect that. Lead is not within that trend though. So that was something that we actually found that we maybe didn't necessarily expect. And it's even more pronounced in lithium if you look at our simulations. And we think this has to do with maybe some electronic valence states, or that there's something different going on in lithium. We don't quite understand what. We know that the total entropy is increasing. That's definitely true. We're not going to violate second law, but we don't have a good explanation for why this happens. We know that it does happen. We do not really know why.
Interesting. I guess you're on this slide. It looks like there is no electronic contribution to the lithium delta.
Yeah, it was basically zero.
Okay.
Yeah, so again, we don't quite know what the origin of this is. I know lithium can have some weird things going on in it generally though. And we really cannot put lithium in a neutron beam though. We would never be allowed to do that.
Yeah. Okay, well, thank you.
Thanks, Adam. Jorge, do you have a question?
Yes, two questions. Camille, this is really nice work. So I guess I was wondering if you could provide a little bit more details on the computational results over here, especially how you calculated, I guess, the vibrational and configurational entropies.
Okay, so if you really want the full details, My colleague Vladimir Lodogin did the actual computations themselves, but we trained these interatomic potentials using a active learning process, using ab initio calculations within VASP. And then we performed a thermodynamic integration over that to kind of say, okay, where's the melting point of this? Took that temperature, was able to use molecular dynamics to generate the velocity autocorrelation function and get the vibrational that way. The total we can get from the free energy, and then the electronic was basically the difference between that and everything else we knew, because we knew the configurational as well. So that's the general workflow of that. There will be more details in the paper when it is hopefully published soon. But if you want the actual details and the parameters used, I would like to refer you to Vladimir.
Yeah, I'll wait for the publication. So I guess my second question is related to that. So I guess when you have these scattering events, almost by definition, you need to have some sort of, because it's giving energy to the photon, right? Creating it or annihilating it. Then there has to be some sort of lattice. And like the sublattice that you showed, I guess the blue and the gray ones, you need to have something like that. But I was wondering, is this still behaving like a single, like an actual phonon, right? I guess a better question will be, can you estimate the lifetimes of these phonons or of these vibrations? I know that you don't want to put them phonons.
So we might be able to, but I don't think it would be straightforward. I know that they are within the time span that we can actually measure with neutrons. And I know that we can get or we can use the velocity that we have to get this. And I know there is work being done for getting these reciprocal space diagrams into a Van Hove type function. And from that, you can get relaxation times and stuff like that. Unfortunately, with the limited Q range here, where we actually can see these, I do think that Fourier transform would just be incredibly messy, and I don't know off the top of my head if this would be enough to do that. I'm sorry.
Yeah, so I guess you have the potential wells over there. I think this would be like a very dynamic potential energy surface. I haven't reached any conclusions. Thank you.
You're welcome.
Thanks very much. I have to ask maybe one last question. Have you used these ideas to actually predict melting? Going back to your one of your very first plots where you have free energy. So you have an energetic component, then you have the entropic component. Can you use these ideas to actually get a better sense of where things melt in terms of temperature as a function of temperature? And then also maybe from the Clapeyron equation, the slopes and the volume changes folded in with the entropy of melting.
So this is something that I haven't explored, and not because I don't think it's interesting, but because I think there are so many different ways to try to predict melting temperatures already that it wasn't as interesting as looking at the origin of this. So I know there are reliable methods to predict melting temperatures, which is usually what people are interested in, of really complicated compounds, organics, and things like that. And so I'm kind of going the other direction and looking at more of the fundamental of like, okay, where's this coming from? can we add compounds to it? And then maybe eventually I'll get up to things like organic molecules and go that direction. So there's a lot more to explore here. I'm not done yet, I don't think. But this is kind of why I'm not looking into, okay, where is this going to melt?
Right. Okay. Well, thanks very much. Great talk and great discussion. So we'll see you next time. Thank you, Camille.
You're welcome. See you next week.